Welcome back. Here we are in part D of chapter 18. This is the part where we're gonna go into the titrations, which like I told you before, a lot of the students on the past think that this is one of the most difficult parts of the course. In my opinion, it is not. It's detailed, and you gotta keep track of a lot of things, but it's mostly stoichiometry from 1411. So I'm gonna try to explain it to you the best possible way I can to see if you can start determining how you can approach it better based on your style. So let's begin by understanding what a titration is. It's usually, we're gonna do it with acid and bases. You can do it with precipitations and other stuff like that, but we're gonna do it for acid and bases. So you can have, for example, a strong acid reacting with a strong base. And as you know from Chem 1411 or General Chemistry 1, this is a neutralization reaction, which is nothing more than a double replacement reaction. So you're going to have H plus, Cl negative, Na plus, OH negative. The positive goes with the negative goes with the positive, so they swap partners. So we get water as one of the products and the salt. So most of the time, typical neutralization reactions, you're gonna get salt and water. Like you already know, others are gonna give you gases, formation of gases. But we are referring to the salt and water formation. On this particular chemical reaction, this reaction is balanced, and you can see that everything is 1 to 1. So you're gonna have your acid in there, a given amount of milliliters. And you're gonna have your base in here. So let's be more specific and follow the one that we're actually doing. And I'm gonna represent basically, if we go back to total ionic equations, we're gonna see that the actual reaction, the net ionic reaction, is gonna be H plus Na plus OH producing water. Notice also that since this is a strong acid and a strong base, there's no equilibrium. It goes to completion. So when you're doing the titration, what you're doing is titrating the protons from the acid with the hydroxide. So as soon as you put the first hydroxide in there, it combines with the acid to produce the water. And as you do that, as you already know, the volume begins to come down. So we began at 40 milliliters. We continue adding hydroxide, which is coming out of the bottom, right? And that combines with the OH to give you another water. And we continue doing that until all of the acid is gone. So we get about 3 more. And ideally, that would have, if we do this right, we will never go underneath the graduation, right? So let's say that we stop there. So that should be enough to cancel everything else that we have. So every proton has been consumed by the base, and we just created more water. So that's all we created, more water there. However, for us to be able to see this, we have to put an indicator there, which is the phenolphthalein you tend to use most of the time. So we have an indicator there that when we put the last one in there, it reacted with this, and that particular compound gave us a change in color. So everything changed color, and you know that that's when you need to stop. So this particular process went from 40 to 50. So you use 10 milliliters. So if you are titrating this, you know the concentration of this. So all you have to do is volume times concentration, and that tells you how many moles of the acid you consume. You probably knew the milliliters of sample that you put, so then you can do moles of the acid over liters of the acid, and you get the concentration of the acid. So notice that when the color change is because you consume all of the acid. So since this is a 1-to-1 equation, the amount of mole of the base that you use is going to be equals to the moles of the acid. So, and that's what we call, that happens at the equivalence point. So that's 1411. So you already knew that. So let's bring it up to 1412. So how do we elevate this to 1412? From 1412, we're going to be titrating a weak acid or a weak base with a strong base or a strong acid. So let's say, for example, hydrofluoric acid, which is a weak acid. We're going to be titrating this with a strong base, NaOH, like any other one. You're using a strong base, so this is going to drive the reaction to completion. So there's no equilibrium. So you're going to get water and the salt. If you notice, we have sodium on both sides. So the actual reaction is going to be, you have fluoride on both sides. So the actual net ionic equation is going to be H plus OH negative, producing water. And then you can say, well, that's exactly the same thing you showed me before for the strong one. So why is this different? Well, this is different because this acid created a conjugate base. So now this is present in there. And because that is in there, that will react with the water, creating hydrofluoric acid and hydroxide. But hydrofluoric acid, the one you just created, is a weak acid, so this will actually establish an equilibrium. So because of that, when you reach the equivalence point on a situation like that, when you are titrating a weak acid with a strong base, at the equivalence point, you are creating hydroxide. So at the equivalence point, the reaction is going to be basic. Remember, you learned on General Chemistry 1 that when you titrate a strong acid with a strong base, the product is water. And water is going to be neutral. So besides talking about equilibrium, what elevates this to a 1412 level? Well, what's going to elevate it to 1412 level is the fact that you can calculate the pOH using the OH concentration, and from there you can calculate the pH. But for you to do that, you're gonna have to use this, and you let me know if this looks familiar to you. You're gonna have to use this. An ice table where you're gonna have your fluoride, your hydrofluoric acid, and your hydroxide, and where this is gonna be, if you started with 5 moles of this, let's say that for example, then you're gonna have 5 moles of this also. However, if you started with 20 milliliters of this and you added 10 milliliters of this, now your volume equals 30 milliliters. So the concentration of fluoride is going to be 5 moles divided by 30 milliliters, and you can change it to liters, right? The hydrofluoric acid is an equilibrium, so we don't know. We know that right at the beginning, there's none of it. There's no hydroxide. But we do know that this one is going to decrease by X. This one is going to go up by X, and this one is going to go up by X. So you can do your equilibriums. This is a base, so then you can do Kb equals X squared over the concentration minus X. And then you can work your magic until you find how much X is, and from there you can find the pH. So a few things that we discussed in there. You're gonna have to keep track of the total volume at whatever point you're trying to find the pH. So at the equivalence point is whatever the sample was plus the volume of the base that you added. You're gonna have to keep track of the moles that are being reacted through stoichiometry and all that. So nothing difficult, but it's a lot to keep track of. So make sure you organize it to whatever method works better for you. So let's begin with this problem. This problem tells us that we have 2 samples were titrated. They were the same volume. They were monoprotic. So in case that you don't remember, this would be a triprotic acid. This would be a diprotic acid. And this is a monoprotic acid. It's basically only one acidic hydrogen. One of them is a titration of a weak acid. The other one is a strong acid. And the same base and the same concentration was used to titrate it. First question, what is the approximate pH at the equivalent points of each curve? For this, we're going to learn something new. You're going to do a graph like this in about 2 more labs using a pH meter. You're basically going to collect the time and the pH, and you're going to be able to build it. And then you're going to get information out of it. As you notice, we're talking with 2 acids, so they are beginning at an acidic level. And then the pH begins to increase, and the pH begins to increase. Notice that on one of them, the slope of my arrow is bigger, so the change is faster, which is A. We can see a faster change on the pH than on this one. So how do we find the pH at the equivalence point? Well, as you notice, when we began to titrate as we add more base. It start becoming basic. It start becoming more less acidic or more basic, and then it jumps. It suddenly jumps from acidic to very basic. That means that the acid was totally consumed, and then you added one drop of a strong base, and that's the only thing in there. The acid is basically became water already. So, so we're gonna use that to our advantage. Because of that jump, we can look approximate more or less halfway. And if you find the corresponding pH, if you find the corresponding pH, that will give you the pH at the equivalence point. So look for the big jump and find the best, to the best of your abilities, find the center of the jump. That's where the equivalence point happens. That's when you added enough base to neutralize all the acid. So you can say that you use about 50 mils of the base on both of them. So for one of them, the pH at the equivalence point is 8. For the other one, the pH at the equivalent point is 7. Which curves correspond to the titration of the strong acid? Strong acid with a strong base only gives you water, so this has to be the strong acid where the titration at the equivalence point is neutral. On this one, it became basic. Does that make sense? Well, remember what I told you. When you did the titration of the weak acid, you created the conjugate base. The conjugate base immediately reacted with water, created an equilibrium that produced hydroxide. Therefore, it makes sense that the pH is going to be basic because hydroxide is being produced at the equivalence point. And with that information, we can decide which one is the weak, which one is the strong. What else do we know? Remember that I told you to pay attention to the slope of the increase? Does it make sense that the weak one have a faster change of pH? Yes, because you are destroying a weak acid, so it's gonna jump faster to basic. The strong acid is gonna fight more. It's gonna produce more protons for the hydroxide to consume it before it changes into basic. So summarizing, if you're giving a graph of a titration, look for the big jump. Halfway in between that jump, that's the equivalence point. And when you titrate a weak acid with a strong base, you can expect the equivalence point to be basic. When you titrate a weak base with a strong acid, you can expect the equivalent point to be acidic. And if this was a test, I would probably tell you that, and I will ask you to show me why it's basic. Show me why it's acidic. That's when you go and start connecting the reactions. This got produced, and this react with water, and that's why it's basic. So let's do some more in-depth problems with this. So let's do this one. We got two samples, both of them the same volume. Both of them the same concentration but different substances. So they're bases. One of them is potassium hydroxide, the other one is acetylamine or CH3H2. And both of them are being titrated with hydroiodic acid, which is a strong acid. So we have two reactions going on. Potassium hydroxide titrated with hydroiodic acid. Strong with strong, so only one arrow. And that's going to give you water and the salt. or the ionic compound, which is soluble. The other reaction is going to be your base. Which is aqueous with the hydroiodic acid. We're using a strong base, so that's going to go to completion, so no equilibrium. And that's going to protonate your base and leave the iodide all by itself. And we knew that we started with 20.0 mils of this, 20.0 mils of this. We also know that this is 0.200 moles per liters. Same story over here. And we know that this is 0.100 moles per liters. 0.100 moles per liters. Okay. And there's a Kb related with this. But I just told you that there's no equilibrium. So let's save that for later, right? There's no use for that right now. And the first question is, what is the volume of added acid at the equivalence point? As you can see, this neutralization is all 1 to 1 to 1, right? So that means at the equivalence point, the amount of a mole of the acid had to be equal to the amount of the moles of the base, because it's 1 to 1, right? So do we know the moles of the acid that we have? Yes, we do. We know that we have 20.0 milliliters. We know that the concentration is 0.200 moles per every 1 liter, which is the same as 1,000 milliliters, right? And that's going to give us 0.004 moles of the hydroxide. Since we know that this is 1 to 1, this is going to be equal to the moles of the hydroiodic acid. Since we know the moles of the hydroiodic acid and we know the concentration, right? 1,000 milliliters for every 0.100 mole, we know that this is going to be 40 milliliters. So to answer the question, you're going to need 40 milliliters of the hydroiodic acid to neutralize that. We are lucky enough that the numbers are exactly the same for the other one, so you're also going to need 40 milliliters of the hydroiodic acid for this one. So we haven't done anything related to 1412. All of this is general chemistry 1, right? Stoichiometry with molarities. So we found out the volume of acid added at the equivalence point. Next question. Is the pH at the equivalent point for each titration acidic, basic, or neutral? Well, we know that the strong one is just producing water and water and the salt, right? And then you can say, well, does having water affect the pH? No, it doesn't. It's neutral. Does having Ki affect the pH? Well, that's a salt, and you know how to deal with that. You know how to evaluate salts to see if they affect the pH. So you're going to have K plus, and you're going to have I negative, and we're going to react both of them with water. This is going to give me KOH plus KOH plus H plus, and this is going to give me HI plus OH negative. So it can be acidic, and it can also be basic. However, before you make any decisions, let's see if this really happens. This is making a strong base. The strong base is gonna go that way. So this will not happen. This is making a strong acid. So same story. That's not gonna happen like that. It's gonna happen like this. So that will not happen either. So the pH at the equivalent point is gonna be neutral, and nothing is gonna affect it because you're making water, right? What about the other one? The other one, you have your base, you are reacting it with the acid, and you are creating your protonated base or your conjugate acid and the conjugate base of the acid. And because this is strong and you carry it until it was neutralized, it's not an equilibrium. However, you created this and you created that. So the moment this goes into the water, you're gonna protonate the water and you're gonna get your conjugate base. So when that happens, you are making the solution acidic. But we also have the iodide, right? Which we already saw what happened here, right? So that's not gonna happen. So this will make it acidic. So at the equivalence point for the strong acid with the strong base, it's gonna be neutral. At the equivalence point for the weak base, by the way, this is gonna be an equilibrium, for the weak base, it's gonna be acidic, which is gonna be less than 7. So that's what we know so far. Next question, which titration curve will have the lower initial pH? So we are titrating a strong base and a weak base. So which one will have the lower initial pH? Lower initial pH means most acidic. This one is a strong base. So this is gonna be very, very basic. So by default, this one will have to be the one that is more acidic or the one with the lower initial pH. So this is basically checking to see if you understand the pH scale. The lower the number, the more acidic it is. A strong base is gonna be a base. So the weak base has to be the most acidic between both of them. And one last question, make a rough sketch of each titration curve. Well, this will be my graph. So I'm gonna have two graphs like this, where I'm gonna be measuring pH on my y-axis and milliliters of hydroiodic acid on my x-axis. I know that the strong one is going to have a pH of 7 at the equivalence point. So I'm going to say with a little bit of inclination, I'm going to try to do this kind of halfway on that line. And the other one, we knew it was basic from the previous problem, right? So we know it was going to be, actually not basic, it was going to be acidic. The weak base is going to make the process acidic. So we know that this one is going to be a little below 7. We don't know exactly how much. We just know that it's going to be a little below. And we try to do it like that also. Something important to remember is that the strong acid is going to experience a bigger change. So let's do that in there. So this change is going to be bigger than the one for the weak acid, for the weak base, sorry. So we also know that right there is going to be equal to 40 milliliters, because that's what we calculated on the first problem, right? So the volume required for the equivalence point is going to be 40 milliliters. And we also know that the weak base have the lower initial pH. So we're going to say, if this, I'm just making these numbers, so don't give too much credit to the number, just to the relative. So this one is going to be a lower pH than this one. And once we go past the equivalence point, we add in the same acid to it. So they should be pretty close. Let's say actually let me take all this back, because we are titrating a base, right? Nothing wrong with doing it wrong, as long as you remember, as long as you can realize that you're doing it wrong, because you move to another step that tells you, oh, that gotta be wrong. So why did I erase everything? Well, I'll tell you in a second. So this is the strong, this is the weak. We're talking about bases, right? So we know that the strong one, the equivalence point is going to be around 7. We know that the weak one, based on the calculation we did earlier, is going to be acidic. So it's going to be below 7. But the part I needed to correct was that we're starting with bases, right? So we're going to start high pH. Then we're going to go through the equivalence point. And then we're going to go down like that. And this one is the strong one. So I'm gonna make it not so pronounced. The weak one, more or less start at the same time. The decline is smaller, and it's gonna be a more pronounced change. So we know that the equivalence point, let me fix that for a second. We know that the equivalence point is going to happen around 40 milliliters for both of them. And that's more or less what we can get. We know that the equivalence point is at 40 milliliters. We determined that on question A. We know that the weak one is going to be acidic at the equivalence point, so we did that. We know that the equivalence point is more or less half the point during the jump. And we also know that the one that have the lower initial pH is going to be the weak one. So the lower initial pH would be the weak one. So this probably would be like a 12, and this probably could be like a 11. Because the weak one, we have the lower initial pH. It's going to be less basic than the strong base. And that's more or less how you do that. But what would you do if I ask you to tell me exactly how much is the pH at the equivalence point for the weak one? How can you do that? Well, let's see. We know that the Kb is that in there, right? So let's do this. So how do I find exactly what is the let me do this again. How do I find exactly what is the pH at the equivalence point? Well, we know that if we began with this base and we titrated with the hydroiodic acid, we're going to get the protonated one, right? Plus the I negative. We already know that this is the only one that is going to react with the water. We know why the iodide is not going to do that. And it's going to create an equilibrium. And it's going to make this environment acidic. Well, at this point, if I can find the hydronium concentration, then I can tell you exactly the pH. So how am I going to do that? Well, we know that Kb equals 4.4 10 to the minus 4, and we know that that's going to be hydronium times the conjugate base over the acid that we created, right? Which means you're going to have to do a ice table where you're going to have your hydronium. Sorry, let's do it the proper way. Where you're going to have your acid, you're going to have your conjugate base, and you're going to have your hydronium. The initial concentration of this, we know that we started with 0.00 moles of this, right? And at the equivalence point, we added 40 milliliters of this, so we have a total volume of 60 milliliters. So you gotta keep track of that, that's super important. So this is gonna be nothing more than 0.004 moles, because it's 1-to-1 over 0.060 liters. There's nothing of this at the beginning. This is gonna go down by X. This is going to go up by X. And then you're going to do your equilibrium concentrations, and then you're going to plug it in there. Then you're going to do whatever you need to do, quadratic X approximation, and so on, and you're going to find your X value. And when you find your X value, you got your hydronium, so you can find the pH. So that's how you will do it at the equivalence point. What about right at the beginning, before you add any hydroxide, any hydroiodic acid? Well, right at the beginning, let me show you the story now. Right at the beginning, like I just said, you haven't added any hydroiodic acid. So the only thing you have is your base in the presence of water, right? Which is a weak base, so that's going to create an equilibrium, and it's a base, so it's going to acquire a proton from the water, and this is going to be hydroxide. You have the Kb, which is what's happening there, right? So by the way, on the previous one, which you have found the Ka, not the Kb. So on this one, you're going to use the Kb, you're going to use the ice table, and you're going to find X, which is the concentration of hydroxide, and then you can do minus log of the hydroxide equals pOH, and 40 minus pOH equals pH. And then you will know the pH at that point. So once more, you're going to need ice table for the initial, and you're going to need ice table for the equivalent points. And you need to keep track of the concentrations of the total volumes and so on. For the initial, your concentration was 0.200 molar, so that's what goes on the ice table. That's how you begin with that. And this is kind of a summary of everything we did. So try to review what I just talked about it. Look at this here until you get a good feeling of it. Like I told you before, not really difficult, but it's time consuming and it requires you to pay attention to everything, attention to details. So with that said, you should be ready to do your daily work, which is basically everything that we had talked about. I definitely want you to show me your work. So that's what I'm going to be looking for on 18.7. And once you do that, pending a lot more practice, then you understand titration in terms of the equilibrium and so on. So next time we meet, we should be finishing this chapter with the last part, which is precipitation products, or KSPs. Equilibrium constant for the solubility product, which is basically what you learned on 1411 about the solubility table, but really understanding why is the table is like that. So until the next one, see you later. Take care.